the matrix of a linear transformation over a finite dimensional vector space, say V, of dimension n, and the matrix that turns out is with respect to an ordered basis. And the size or the order of this matrix is n by n rows and n columns. We had also proved that a matrix say of order n by n with entries from F, where F is a field, can be treated as a linear transformation over some vector space V. And this vector space V can be taken as Fn over F, where Fn is the set of all n tuples, entries coming from F. Now, this linear transformation could be defined as the image of V under T, say, for example, if you call this as T, is VA, where VA denotes the product of the row vector with the matrix A. So row vector means this is of 1 by n order matrix, and A is n by n, and we know already we have defined how to multiply two matrices. This becomes 1 by n matrix, and so is again a row vector. Now this mapping becomes a linear transformation. That also we had already proved. And we also know that linear transformation is completely determined if we know the effect of the linear transformation over its basis vectors. So this we had already done. So that sets up one-to-one linear one-to-one correspondence between the algebra of linear transformations over a vector space V of dimension n, and the dimension of this algebra is n square. And this algebra is an associative, it contains identity also. On the other hand, we also know by now that the set of all n by n matrices with entries from F is also an associative algebra with identity. And the dimension as a vector space of this algebra over F is also n square. We had also proved that the two algebras are therefore isomorphic onto each other. And one such isomorphism can be obtained by defining the map which takes a linear transformation T to its matrix with respect to an ordered basis B. So this is what we have already proved. Now what next we can see here, because of the one-to-one correspondence, every linear transformation we shall be identifying by its corresponding matrix with respect to an ordered basis, and this ordered basis more often is taken as the standard basis. Likewise, the algebra of matrices also have a standard basis. And this basis consists of matrices of the form EIJ, where the matrix EIJ is of order n by n, and the entries are 0, except only one entry which is non-zero, and this entry is 1, and that appears on the intersection of ith row and jth column. These matrices are n square in number, and they form a basis that can be seen easily, and this particular basis is known as the standard basis for the matrix algebra MNF. We also had proved that AVF is a general linear algebra of linear transformations of the vector space V. Now, any algebra is isomorphic onto a subalgebra of this algebra AVF that we had already proved. Now, this algebra becomes, AVF becomes isomorphic onto MNF, and therefore any algebra or subalgebra of matrices, subalgebra of M and F of matrices, is therefore isomorphic onto a subalgebra of the algebra of matrices, namely M and F. So this is what is to recall what we had already done. Now, one more important theorem that we want to prove is about the similarity. So similarity so let us say V is a finite dimensional vector space. So let us take a dimension of V over F in Pn be finite. And T and S are two linear transformations. That means that they are members here, ABF. Nice, good. Now we say that S is, so we say then S is said to be similar to T if there exists a regular linear transformation U in A over F such that S is U T U inverse, or you can also change U by U inverse, then this is U inverse T U. Regular means U is invertible and is a linear transformation. Now, it is easy to see that similarity is actually an equivalence relation. So you can prove easily that similarity is an equivalence relation. A relation is said to be equivalent if it is having the property of being reflexive, symmetric, and transitive. And it is easy for you to verify that this is an equivalence relation. Once we have an equivalence relation on a set, then correspondingly we have equivalence classes. So equivalence class with respect to this equivalence relation of the linear transformation T is what? So it consists of all linear transformations in this S and V such that S is similar to T. So S is similar to T. That means what? There exists some U in AFV such that S is UTU inverse or U inverse TU, whatever you want to say. Or also is the same as this class. So this is the class of T. Class of T is therefore is also same as. So this is UTU inverse. UTU inverse, where this U is regular transformation. All with that U in AFV is regular. So is the set which consists of linear transformations, say UTU inverse, where U is regular, then this is the equivalence class of T. So, for example, if 0 is the linear transformation here in AFV, the class of the 0 linear transformation will consist of what? Now, you can see that for every invertible linear transformation, U0 U inverse is again 0. So it consists the 0 linear transformation. Likewise, you can also see if I is the identity linear transformation, so for the linear transformation, identity linear transformation means it maps so V onto V itself. The class, therefore, of I will consist of what? All U, I, U inverse. And therefore, this is I only. So this also consists of only one element. Class of, say, alpha I, where alpha is an element of F, then becomes a linear transformation. So is therefore is U alpha I and then U inverse. So what you see here is that alpha U alpha. So this is the same as alpha I, because alpha I always commutes with every linear transformation. So this is the same as alpha I. And this happens for every alpha here in F. So in particular, when alpha is 0, that was the class of 0. And when you see the class of alpha being equal to 1, class of I is I. And that happens actually for every scalar matrix, that the class of the equivalence class of alpha I consists of only one element, namely alpha I itself. But that may not be the case for other linear transformations. It will be interesting to see when the class of linear transformation T. So this is for you to see. Find T in AFV such that the class of equivalence class of T is consisting of only T only. Now, this class definitely has elements. Okay. If nothing else, it has T only. So when is it the case that there is no other matrix other than matrices? So since this AFV to MNF, T being sent to the matrix of T with respect to an ordered basis B is an isomorphism of AFV onto MNF, where what is N? N is the dimension of the vector space V over F, and B is an ordered basis. For V over F. So since this is an isomorphism, what we get is we can define likewise for two matrices, say A and B, the matrices, so M and F, that B is similar to A, we call it that B is similar to the matrix A, if there exists an invertible matrix, say U, if you want, you can call it something else. So why U? An invertible matrix, so P here in M and F, such that B is equal to PA, P inverse, or P inverse AB. That is just you can replace P by P inverse. And once again, we get the classes. So the equivalence class, therefore, of A is the set of all matrices B, such that B is similar to A. And this is same as, you can see, PAP inverse for every this P in AFV. So now it will be M and F. And P is regular and P is invertible. So once again, now you can see that the class of, so you can verify that the class of alpha I, the scalar matrix, is the same here as alpha I. This consists of this. So equivalent, of course, exercise could be find all matrices B here in M and F, such that the class of B is just consisting of one element. Okay. So we have now an equivalence relation on the algebra of linear transformations, and also equivalently we also have the equivalence classes on n by n matrices with entries from F. Now, one important result is that you can prove, if you are not already, that if S is a set on which there is an equivalence relation defined, then this can be seen as disjoint union of classes of S. So class of, say, the element S in S, and this disjoint union, this union runs over equivalence classes. Equivalence classes. S. Now, any two classes are either, since any two classes are either disjoint or identical. We get, what do we get is that S is the disjoint union, means here say S, class of S. So class of S, class of an element S, and S runs here. So the union is over disjoint classes. So as only one element is taken from each disjoint class is over disjoint classes by taking one element exactly from each class. And therefore, to study linear transformations, or for that matter, matrices, it is better to study the equivalence classes. So we need to know, therefore, the class of a linear transformation or the class of a matrix. And therefore, what becomes important is whether, so for example, is P in the equivalence class of A in MNF. In MNF. That is, does there exist an invertible matrix here U MNF such that B is equal to U A U inverse or U inverse A U. Now, for linear transformations, the likewise, you can say is S in the class of T in AFV. That amounts to saying that does there exist a regular linear transformation T in AFV such that S is UTU inverse or equivalent for ST in AFV. Does there exist, say, U in AFV such that S is UTU inverse? That means is S similar to T or is B similar to A? And if there are similar matrices, then what could be U? So this finding out the matrix U or finding out a linear transformation U, which is regular and has this property, that becomes quite interesting. So this is just for you to have a look at. 1 second. Okay, so recall the theorem that we have proved that V is the theorem. Let us take V over F, the dimension, V over F be n finite. V is a vector space and F is a field. V is of dimension n. And let us take T to be a linear transformation here in AFV. Then what we have already proved that AFV is isomorphic onto MNF. Good. How this map is that T goes to the matrix of T with respect to an ordered basis B. For the vector space V over F. Now, if we change the basis, then what happens? So, let us take here further. If B1, B2 are two ordered bases, for V over F, and you can also take the entries you want. Then the matrix of T with respect to the ordered basis, say B2, and the matrix of T with respect to an ordered basis B1, they are related by, so this is what here, so this is, you can call that this is your says, a matrix here says C inverse. For some invertible matrix C in MNF. In M and F. Okay. So when we change the ordered basis, the relationship between the two matrices with respect to these bases is as follows. So we want to now prove this. So the proof is as follows. So suppose let us take one ordered basis has the elements say V1, V2, Vn, and another is say W1, W2, Wn. So let us take V to be the ordered basis, so V1, V2, say Vn, and let us, sorry, this is B1, V1, B1, and B2, let us take entries, say W1 to Wn. Suppose these are the two ordered bases. Now define a map now here, a linear transformation, say in AFV, such that it maps basis vectors to the basis vectors. Say VIS is WI for every I 1 to N. Now this linear transformation can naturally be determined by taking the images of basis vectors under S. And suppose we have this TB1. Now TB1, say, now let us take, say, TB1. Yeah? So I call it, say, A. The A, and the entries, let us take alpha ij, n by n. So alpha ij is R from F. And also call, say, TB2 as B, and the entries, let us take beta ij, n by n, and beta ij to F. What does it mean? That means, so that's how we have defined that each VIT is a linear combination here of VJs, alpha ij, Vj, j is equal to 1 to n. And we also know about the WIT. WIT is beta ij, Wj, j is equal to 1 to n. You can change the index also if you want. Now, one thing is clear that since this maps, S maps basis onto basis, so this is an onto linear transformation. And for a, now, as in AFV is onto, as it maps basis vectors onto basis vectors. Basis vectors onto basis. So basis onto basis. Vectors, it means that. So this linear transformation is onto, and V is finite dimensional. Dimension over F over V is finite. What we get? S is invertible. Because for a finite dimensional vector space, we had already proved that such a map will be one-to-one also, and therefore invertible. So then this becomes then P is 1-1 also, and hence S is 1-to-1, and hence S is regular. S is invertible linear transformation. Okay. So we have got this. S inverse exists. Now this VIS is equal to WI will give us interesting thing. So now VIS is WI. All right. Now VIS here, so if you, S is invertible, and WIT and WIT. WIT is because the matrix of T with respect to the ordered basis B2 that we already know is B. So this is beta ij and Wj. J is equal to 1 to n. Is equal to 1 to n. VIT is also we know is alpha ij from the earlier page. Vj, j is equal to 1. So this is what we have now. Now, since S is regular, so ST S inverse also makes sense. Since S is regular in AFV, STS inverse is also a linear transformation. Now we want to see the matrix of STS inverse with respect to the ordered basis B1. So the matrix of STS inverse here with respect to the ordered basis B1. With respect to the ordered basis B1. This becomes the matrix of TB2. Why is so? You can see that for VI under ST, for example. First, take this. So VI under ST is VI under S and then T. VIS is WI under T. WI under T is beta ij. Just a second. WI under T is beta ij WJ. Beta ij WJ. Now, what is here we have? So, this is the sum over J. J1 to N. So, the WJ is VJS. So, beta ij VJS. So, this is the same as summation J is equal to 1 to N. Beta ij Vj, because S is a linear transformation S. Now, S is invertible. So, what we get here is apply on both sides. So, VIST and then S inverse. This is same as J is equal to 1 to N, beta ij, and this is here Vj. So, Vi under STS inverse, this is beta ij, Vj. Now you can see that this composition of this linear transformations is associative. So this is same as Vi under STS inverse. STS inverse is same as beta ij Vj. J is equal to 1. Now, this is what we have STS inverse. So, this is or that STS inverse, because this is associative. And when you operate this on VI, so this becomes your beta ij. So, this is summation beta ij Vj. J is equal to 1 to N. This. And so the matrix of here STS inverse with respect to the ordered basis B1 are these entries, no? This beta ij n by n. And this is what? This is the matrix of T with respect to the ordered basis B2. So what we have got here is the matrix of the STS inverse linear transformation with respect to the ordered basis B1 is actually same as matrix of T with respect to the ordered basis B2. Now recall since this map that takes T to this matrix with respect to the ordered basis B. This map is an isomorphism. We get that the T1, T2 are two linear transformations, and T1, T2B same as T1B, T2B for every linear transformation T1, T2 in AFB and ordered basis, and for every ordered basis B for V over F. This also gives for a regular linear transformation, say U in AFB, that the matrix of identity that we know is basically identity matrix of the identity linear transformation. Say U, and this is U inverse. This is the matrix of U and the matrix of U inverse. And you can also see that if you write here for U inverse U, so this is also same as U inverse U. So you have U inverse or U inverse U as identity. So that makes that here the matrix of U. So this is with respect to ordered basis B, 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 B. So this is here that this matrix of U inverse with respect to the ordered basis B is actually the inverse of the matrix with respect to this ordered basis B. So we apply here this. So STS inverse here TB2. So what we have here TB2 is the matrix of STS inverse with respect to the ordered basis B1 is same as, so matrix of S with matrix of T, matrix of S inverse, each of them with respect to ordered basis B1. We also see here the matrix of this B1, matrix of TB1, and this is same as the matrix of S with respect to this B1 inverse. Now you can take this U to be here. If you want to write in terms of the, if you want to take this, or C, we call it C, so call it C. So let us take C to be the matrix of this with respect to the ordered basis B1. What we get is, so this is B is here CAC inverse. This is also same as C inverse AC inverse. So So you can call if you want that this is say C as C inverse. If you replace and you make its inverse, so this also will go away. So this will be simply C. So this is here P inverse AP, where P will be C inverse. Or B is equal to this. So this theorem therefore gives us the relationship between the matrices when we change the basis. And it is for this reason this matrix C is called the matrix C is called the matrix of change of basis. And this is the matrix of the linear transformation S, which maps basis onto basis. You can recall these we had already computed. So these you can check about, for example, let us take V to be the vector space. Here say V4. So what is the vector space? So V4 is the polynomials in Fx, such that degree of Fx is less or equal to 4. And take B1 as the standard basis. So this is 1x, x square, x cube, and x4. And another basis that you can also prove, we had already proved actually, 1 plus x square, 1 plus x cube, 1 plus x4. Then B1 and B2 are two ordered basis for V over F. F you can take as R. And Vi is, let us call that Vi is x power I minus 1. And let us take Vi to be x power I minus 1. And Wi say 1 plus Vi. That's what it is here for every I, 1, 2, 3, and 4, and 5. So like that, these are 5 basis vectors. And as be the linear transformation that sends, so in AFV, that sends Vi as Wi for every I, 1, 2, 3, 5. Then the matrix of the linear transformation D from V4 to V4 is Fx being sent to Fx of under D. The derivative of this Fx is a linear transformation of U. Good. We had already obtained the matrices with respect to these bases. So I will straight away write from what we had already proved is that the matrix of D with respect to the ordered basis B1 is a matrix 5 by 5. So this is what it is 0, 0, 0, 0, and 0. So you can say, okay. And the next row is 1, 0, 0, 0, 0. And then you have 0, 2, 0, 0, 0, 0, 0, 3, 0, 0, 0, 0, 4. 0, 4. Yeah, अंदर नहीं करना. DB2 is 0, 0, 0, 0, 0. One, 0, 0, 0, 0. Then minus 2, 2, 0, 0. Minus 3, 0, 3, 0, 0. Minus 4, 0, 0, 4, 0. This we had already obtained. Now, the matrix of S we want to write. So, with respect to the basis B1. So, to know the matrix of S with respect to the ordered basis B1, we need to know what is VIS. VIS as a linear combination. Here, VIS as a linear combination in the linear span of B1. That's what we want to know. Now, what is V1S? So, V1S is 1S. The derivative here, so this is W1. So W1, so this is W1. W1 is 1. So this is same as V1. V2S. V2S is W2. This makes what? So this is equal to, so this is W2. W2 is equal to 1 plus X. Or 1 plus X. This is 1 plus 1 is this. So V1 plus V2. V1 plus V2. Then V3S is W3. W3 is what? 1 plus X square is 1 plus V3. V4S is 1. So this is V1 plus V3. And you can check that this is V1 plus V4. And V5S is V1 plus V5. And so C is the matrix here with respect to ordered basis B1 of S. And that gives me, therefore, so since V1S is V1, therefore the first row is 1, 0, 0, 0, and 0. Second one is here, V2S is V1 plus V2, and therefore this is 1, 1, 0, 0. V3S is V1 plus V3, so V1, 0, 1, 0, 0. V4S, V1 plus V0, 0, 1, 0. V5S, 1, 0, 0, 0, and this is 1. So this is the matrix 5 by 5. You can see that C is invertible and B is C inverse. So this is what it is, that the matrix of D, therefore, with respect to the ordered basis B2, we have got here is C, and this is here matrix of D with respect to the ordered basis B1, C inverse, where what is C? C is as B1. So this is one example that we had already seen. So you will have plenty of examples to track of the time. So this is already the time. So we shall wind up here, and tomorrow we shall take up few more examples for the change of basis. So thank you very much for your kind attention.
Thank you, sir.